Throughout our discussion of periodic behavior of atoms that's upcoming, we're going to learn that much of the reason why atoms behave the way that they do is a consequence of something called their effective nuclear charge. And it's sometimes abbreviated as ZEF, a Z with a subscript EFF. Z being a reference to atomic number, a number of protons, and EFF, of course, referring to effective charge. Now, what this is fairly simple to understand. You have an atom which has a nucleus, and in that nucleus there are protons, and protons have positive charge. Now, surrounding the nucleus you find electrons, small bits of matter of negative charge. And the reason the electrons don't just wander away is because the nucleus exerts an effect on these electrons. There's an attraction between positive and negative charge. And so how great this attraction is part of what effective charge is all about. What's the effect of the nuclear charge on electrons? But the electrons we're going to examine when we talk about effective nuclear charge are the most important electrons, the ones that react with other atoms, and those of course are the valence electrons. The electrons having the highest principal energy level, the outermost electrons, the ones that are hanging out well outside the atom, so if some other atom comes along, it's these electrons that interact with the other atom. So when we're talking about the effect the nucleus has on electrons, it's really the valence electrons that we care about. How great a pull or how great a control does a nucleus have over its valence electrons? And that really depends on only two things. The first thing that this attraction depends on is how big the positive charge in the nucleus is. And that, of course, is a function of how many protons there are in the nucleus. Because, of course, I would expect that if a nucleus had a plus 10 pull, 10 protons, instead of just one, an electron would be far more attracted to the nucleus. There would be a much greater effect on this negative charge if there were 10 positive charges instead of one. So the number of protons plays a tremendous role in the effect the nucleus has in controlling its valence electrons. However, there's another thing that helps mitigate that effect, reduce that effect somewhat, and that is other electrons. Because if there were other negatively charged particles between the nucleus and the valence electrons, these negative charges repel that negative charge. And even if the nucleus is attracting it, the repulsion from these not valence electrons, if this were an outermost valence electron, these would be non-valence electrons. That pull of the nucleus is reduced by these. So the number of non-valence electrons can reduce the effect of the nuclear charge. So to calculate an effective nuclear charge is pretty simple. We can even think of it in terms of an equation. If you know how many protons there are in the nucleus, then you know what the positive pull on the valence electrons would be. Likewise, if you knew how many non-valence electrons were blocking that pull, you could reduce the effect by that number of electrons. We call these sometimes shielding electrons because that's what they're doing. They're literally shielding the nucleus from the valence electrons. And so, as an example, if we were to pick an atom, say neon, neon has a 1s2, 2s2, 2p6 configuration for its electrons. If I looked at a periodic table, I would see that it has 10 protons in its nucleus. And therefore, we'd have a plus 10 pull in the nucleus of neon. And this is for neon, just to remember. And of course, the electrons that we're interested in determining how much of an effect this is are these. The valence electrons, the ones in the highest principal energy level, that being n equals 2 for neon. So of course we would think of there being 10 negatively charged particles out here somewhere, and the nucleus with a plus 10 pull here, but in this case there would only be 2 non-valence electrons, 2 electrons shielding the nucleus from these outer electrons. Therefore, simple to calculate the effective charge. A plus 10 pull from 10 protons minus 2 electrons shielding these electrons from that nucleus, and that is a plus 8 effective charge for neon. Now, coincidentally, or not coincidentally actually, if we look at a periodic table, neon's in group 8, main group 8. And yes, the effective nuclear charge for neon was plus 8. Now, I wonder if that's true of all atoms. If I know what group they're in, main group, can I determine their effective charge without actually calculating it, just by looking at the periodic table? And the answer to that is yes. If I were to say pick magnesium, I could automatically assume the effect the nucleus has on the valence electrons is plus 2 because it's in main group 2. And now I can actually demonstrate why. The configuration would be 1s2, 2s2, 2p6, and 3s2 for magnesium. And of course that means that these 2 electrons are the valence electrons that we're interested in the nuclear effect on. And it makes all 10 of these found in lower principal energy levels. These are shielding electrons, blocking that effect. So if magnesium has 12 protons, there's a plus 12 pull from the nucleus minus the 10 shielding electrons, which reduce that pull. Therefore, the 2 valence electrons would feel a plus 2 pull from the nucleus. And just to reiterate that this isn't just some fluke thing with magnesium, I'm randomly going to pick phosphorus. I know it's in group 5. I anticipate that its effective charge is going to be plus 5. Let's see. Well, phosphorus has a 1s2, 2s2, 2p6, 3s2, 3p3 valence. Well, it's got 3s2, 3p3 as its valence configuration, but this is the entire configuration. Now it has 15 protons in the nucleus, exerting an effect on these valence electrons out here. But that means these 10 non-valence electrons block that effect, and plus 15 minus 10 is a plus 5 effective charge for phosphorus. So yes, any main group element that's neutral, we're talking about neutral atoms, has the same effective charge as its group number. So then you might ask, well, how about the transition metals? What are their effective charges? And it's important to recognize that almost all of these transition metals behave just like group 2 atoms. And therefore, I'm not surprised if I find that almost all of them have a plus 2 effective charge. As a random example, pick nickel. We know nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8 as a configuration. But again, when we're looking at the effect the nucleus has on valence electrons, we care only about those 2 electrons, which are valence electrons. So with 28 protons in the nucleus, but 2, 4, 10, 12, 18, 26 non-valence electrons reducing the effect, it's plus 2, the effective charge, just as you'd see for a group 2 element. And of course there are exceptions, and that's because some atoms disobey Aufbau. Namely, if I wanted the effective charge on copper, I know that since copper behaves like a group 1 atom, it's going to be +1. And that's because, of course, copper has argon's core, 4s1, 3d10. Remember, it's an exception. It likes to fill and half-fill at sublevels. And that means copper only has one valence electron, and these 18 in the core of argon and these 10 end up making 28 total shielding electrons. So copper has 29 protons and a total of 18 plus 10, 28 shielding electrons. Yes, it has a +1 effect. So if it's as easy to calculate effective charge as simply looking up a main group number, why do we need to know how to calculate it? Well, that's because we've only talked about neutral atoms. What if we look at an ion? And I'll randomly pick the calcium ion. Now, I know that calcium, the atom, would have an effective charge of +2 because it's in group 2. But calcium, the ion, is a very different story. And that's because it has a 1s2, 2s2, 2p6, 3s2, 3p6. But don't forget, these two 4s electrons are lost in oxidation to form the calcium +2 cation. So in fact, the calcium cation is isoelectronic to argon. It has the same configuration of 18 electrons as argon. And so now, look what happens to the effective charge. Yes, calcium still has its 20 protons. It doesn't lose protons, it loses electrons to form the ion. And now I need to reduce the effect on the valence electrons by the number of non-valence electrons. But look, these are the valence electrons for calcium cation. They were actually the 4s electrons for the calcium atom, but these are the ones that are feeling the effect of the nucleus once those two 4s electrons are gone. So that means the number of shielding electrons in the atom is only 10. And therefore, these valence electrons would feel a +10 pull from calcium's nucleus. Very different than the electrons in neutral calcium felt. But those electrons were out here in the 4th principal energy level and had all 18 of these shielding them. And 20 minus 18 was +2. So yes, the neutral atom has a +2 effective charge, but the ion, which loses that valence level, effectively making n equals 3 the valence level, has only 10 shielding electrons shielding the nucleus. So a very different effective charge. So then you might ask, how does adding electrons to a neutral atom, thus creating an anion, affect the effective charge? And the answer is it doesn't. An oxide ion will have the same effective charge as an oxygen atom, +6. And here's why. If we look at neutral oxygen, this is its electron configuration, which means that these 6 valence electrons right here are the ones feeling the effect of the nucleus, +8. And the only thing shielding them from the nucleus are these 2 electrons. So yes, neutral oxygen has a +6 effective charge. Now simply adding 2 more electrons has no effect on that pull, and that's because we add the electrons to the valence level, not the non-valence level is shielding electrons. So the oxide ion still has 8 protons pulling on more valence electrons, but only 2 electrons are still shielding those additional valence electrons, so they still feel a +6 pull.